Greetings, ladies and gents, and welcome back. It's Mike Mates and Science Club. In the previous video, we introduced the concept of momentum, and we said that momentum is the product of an object's mass and its velocity. And we also discussed about the change in momentum of an object. Now, in this video, we'll be taking things a little bit further. I will be going through what is known as impulse and Newton's second law in terms of momentum. So let's just start with impulse and just build it from there. So what is impulse? So we say that impulse, which doesn't have any letter or any symbol to present it, by the way. So we say that impulse is the product of the net force and the time taken over which the force acts on the objects. Now, unfortunately, in this video, I don't want to make it a very long video. I'm not gonna write the definition down. So in this case, I'm simply just going to say it, and then in this case, you can write it down. This is very important because these definitions, they normally come up, quite a lot, and they occupy about 2 marks each definition. So in this case, we say that impulse, right, is the product of the net force and the time taken over which the force acts on the object. So mathematically, we say that impulse, right? Let me just, all right. So we say that mathematically, impulse is actually equals to F net multiplied by the change in time. So in this case, now remember, we said that when you take a vector quantity and you multiply it by a scalar quantity, the result that you always get in this case is a vector quantity, right? So what I'm simply implying with this is that impulse is a vector quantity, meaning that when they ask you to calculate impulse, you must also always express it in terms of its magnitude and in this case a direction. Now the good thing about impulse is that impulse is actually always in the direction of the net force. So if you know that the net force is going to the left, so that would mean that the impulse in this case would also be to the left. If in this case, if the net force is acting to the right, so that would mean that the impulse would also be in this case to the right. Now the SI units for force, we know that of course measured in Newton, and in this case the SI units for time is always measured in seconds. Now what you need most interestingly, the SI units also for impulse is actually Newton second. So those are the SI units for impulse. So impulse is actually it's SI units, it's Newton second. So that's what you need to note. Now remember the definition, you must just have that in your mind. So now we say that we say that impulse in this case is the product of the net force and the time taken which the force over which the force spends in contact, in this case with the object. Now what we're going to do, we're going to take a quick example for this, which I've prepared. So in this case, they say that a 2 kg trolley moves in a straight line with an initial velocity of 5 meters per second. To the right, they say that a constant force of 10 Newton acts on the trolley for 0.4 seconds, causing its velocity to change in this case to 3 meters per second to the right. Let me just put that out there so that we have more space. So in this case, they say that calculate the impulse acting on the trolley using force and in this case time. Now we know that of course we have a trolley, right, that is moving to the right. So in this case, there is a force that is constantly acting on this trolley that caused the trolley in this case to lose its velocity from 5 in this case to 3 meters per second in this case to the left. So in this case, what I'm going to do, I'm going to choose going to the right as positive, so that would mean that to the left would be a negative. So we know that of course that force there would be opposing, right, the motion of the trolley, meaning that in this case it would be to the left. So in this case, what I'm going to do would be to say impulse, right? So that's impulse. So impulse is actually equals to F net, right, multiplied by delta t. So in this case, what we have, we know that F net in this case would be negative 10, right? So in this case, we would have time is 0.4 seconds. So in this case, if you put that in your calculator, the answer that you are going to get is actually negative 4 Newton second. Now remember, we said that negative there, it actually, now remember we said that impulse is a vector quantity, meaning that you must express it in terms of its magnitude and direction as well. And that negative there, it tells us the direction in this case of impulse. Now we actually already knew, of course, the direction of impulse, because I said that the direction of impulse is always in the direction of the net force, right? So in this case, that would simply be actually equals to a 4 Newton second. In this case, to the left. Right, so that's what we have here. Now you might be wondering, why did the question specifically say calculate impulse using the net force and the time? Now, is there another way to calculate impulse? And the answer to that is yes. Now remember, we say that impulse is the product of the net force and the time taken over which the force acts on the object, right? Now, most importantly, impulse tells us how an object's momentum changes. It tells us the change in momentum of an object. So what I'm implying right now with this statement is that impulse is the same as an object's change in momentum. So what I'm simply saying in simple words is that impulse is actually equal to an object's change in momentum, and we have a formula for that, which says, now remember that let me just put let me just scroll down. So remember I said that impulse is actually equal, right, to an object's change in momentum, meaning that we know that force impulse, so we know that impulse is actually equal to, in this case, F net multiplied by delta t. But again, I mentioned that impulse and change in momentum, they're equal, right? So in this case, this will simply also be equal, in this case, to delta, in this case, p, which is the change in momentum. So in this case, we actually call this the impulse momentum theory. So this is, let me just write that. So that's the impulse momentum theory. So that's the theorem. So that's the impulse momentum theory. So in this case, so impulse and change in momentum, they're exactly the same thing. They represented the same physical idea, they're just expressed into two different ways. So if you're not given time and also you're not given the net force, and they ask you to calculate the impulse of an object, then what you can simply just do would be to calculate the object's change in momentum. And in this case, you just simply say that's in this case that's your impulse. Why? Because in this case they're exactly the same thing. They're just expressed into different ways. Now let's just go back to this example that we were doing, and let's see. Now let's see if that the answer that you're going to get if you calculate an object's change in momentum. If let's try to find out if we are going to get the same answer, in this case as -4 Newton per second. So in this case, or Newton second rather. So in this case, what I'm going to do, I know that force impulse. I know that in this case impulse, right? So we know that impulse is actually equal, in this case, to F net multiplied by delta t. But also this is actually equal, in this case, to the change in momentum. So in this case, I know that this simply be equals to the change in momentum, right? So what I'm going to do would be to calculate the change in momentum of that object. So in this case, what I would have would be mass multiplied by, let me just do that from that last step. So in this case, what I would have there would simply be, in this case, mass multiplied by Vf minus Vi. Right, so in this case, I know that the mass in this case is 2, so that will be 2 open bracket the final velocity. Now in this case, they say that the final velocity in this case was 3 meters per second to the left, meaning that the final velocity in this case would be negative, since we chose going to the right as positive. So in this case, this would be -3. So this would be -3 minus, so this minus is actually part of the formula, so this would be minus, in this case, 5. And if you put that in your calculator, unfortunately what you're going to get would be -16 Newton second. Now this cannot be right. Now this means that something is wrong somewhere here. Let's just check carefully if, of course, if we did something wrong, or if the question itself did something wrong in the process. So if the impulse from the net force and the time is -4 newtons per second, then this tells us, according to that law that we have here, this tells us that the change in momentum of this object should be -4 kg meters per second, right? Now this means that the final velocity, the given final velocity, is inconsistent with the force and time provided. Now let's just simply check what the final velocity should be, since we know that the change in momentum should be negative 4 kg meters per second. Let's just see if the final velocity we actually come up to be the same as 3 meters per second, in this case to the left. Now let's just check. Now we know that, of course, we know that impulse is actually the change, of course, a change in momentum should be negative 4. Right? So in this case, what I'm going to do would be to say that change in momentum, so that would actually be equals to mass multiplied by Vf minus Vi. Right? So in this case, I know that change in momentum should be, in this case, negative 4. So in this case, this would be negative 4. All right, so this would be negative 4 equals to the mass, which is 2. So in this case, the final velocity is what I'm trying to check. Right, so in this case, what I have in this case would be Vf, in this case, minus the initial velocity, which would be 5. So in this case, if I divide by 2 on both sides, so in this case, what I would have would be negative 2 being equal to Vf minus 5. And of course, if I transpose that negative 5 to the other side, so what I would have eventually would be Vf being, in this case, so we know that negative 2 plus 5, that's 3. So this will simply be 3 meters per second. In this case, since the answer is positive, so that would mean that it's 2 to the right. So the trolley slows down, but in this case, it does not change the direction. Now, what was my point here? I did this deliberately, by the way. So my point here was for you to note that the impulse calculated, using Fnet multiplied by time must equal to the impulse that you get when you use the change in momentum, in this case, or when you calculate an object's change in momentum. So if your impulse doesn't match in this case, then this simply tells you that your physics is lying to you. So in this case, what I'm going to do, so in this case, we verified that, of course, the direction in this case was wrong. So in this case, this was supposed to be to the right. Right, so in this case, we know that this was not, so let's just recalculate the impulse in this case. So we know that for impulse would simply be equals to, in this case, an object is changing momentum. So in this case, this would be mass multiplied by Vf minus Vi. So in this case, we know that the mass in this case would be, so it would be 2 multiplied by Vf, which is, this case is 3. Right, because we verified that in this case the trolley slowed down, but in this case it did not change. It did not in this case change its direction. So in this case it would be positive 3. It will still be to the right. So in this case this would be minus, in this case, 5. So in this case, what we would have there in this case as our answer, it would actually be negative 4. All right, so in this case it will be negative 4 Newton a second. Right, and again you can note we are actually at the same position there. So in this case, what we would have there would be 4 Newton second. In this case, to the left. So in this case, so my point here was for you to know that the impulse calculated using in this case Fnet multiplied by time must equal to the impulse calculated using the change in momentum. So in this case, impulse doesn't care actually how you calculate it. If your answers doesn't match, then your physics is lying to you. I hope that makes sense. So that means that this what we were doing here was actually wrong in this case. So in this case, our answer would still be in this case it would be 4 Newton second. In this case, 2 in this case to the left. Right, now we also have a graph in this chapter. All right, a force versus time graph in this case. So in this case, now this graph is actually very important. It is actually very important things, in case it comes up, it kind of pops up there and there. So let's just do it. You may never know, if the examiners might just also put it in the exams. So we have this type of graph, which is actually a force versus time graph. Let me just write that. So we have just draw a line there. So in this case, we have a force. Oh, that's not force. So we have a force. In this case, versus time graph, which actually looks like this. It looks actually more or less like that. All right, so that of course would be this case. So this type of graph, it actually looks like that. So in this case, this would be this would be the Fnet. In this case, in Fnet, in this case in Newton. Right, in this case, would have our x-axis, in this case is time, delta t, but in this case in seconds. Right, so in this case, if you note very importantly, about this graph, you know that what we have here is actually, you know, a triangle where the base in this case is time and the height is the force. Now, very interestingly, the area under this graph, it actually represents impulse. Now, if we were to calculate the, you know, the area of this graph, so what we would have in this case, let me just erase that. So in this case, what we would have would be, in this case, if we were to calculate the area of that, so in this case, what we have would be area. So that would actually be equals to half. Now, how would we calculate the area of of a triangle? So what we do in this case would be to say half base times the perpendicular height. So in this case, we would have half multiplied by the base multiplied by the perpendicular height. So in this case, so this would be a half, right? The base in this case would be time. So this would be multiplied by delta t multiplied by, in this case, the perpendicular height would actually be represented by the force. So in this case, this would be multiplied by F net. Right, so in this case, if we can note that we have this expression here, which actually is the expression for, in this case, for impulse. So in this case, if we now remember that time multiplied by net force is actually the same thing as the force multiplied by time. You know that multiplication is commutative, right? So in this case, what would have there would simply be it would be, in this case, a half. In this case, multiplied by F net multiplied by time. So one thing that you must note about this graph is that the area underneath this graph, it actually represents the impulse of an object. So in this case, if they ask you for an impulse for the impulse of an object, so what you can simply do would be to calculate the area, right, of this graph, and then you just say that's your impulse there. So in this case, what you're going to do, again, we're going to take a quick example for this. So they say that the following graph shows the force exerted on a hockey ball over time. They say that the hockey ball is initially stationary, meaning that its initial velocity is 0, and they say that it has a mass of 150 grams. So they say that calculate the magnitude, in this case, of the magnitude of the impulse of the hockey ball. Now, again, remember we said that, of course, if we have this type of graph, so in this case, to calculate an impulse, what we would do in this case would be to calculate the area, right? So in this case, we would know that this impulse, right, would simply be equals to, in this case, to the area. So in this case, which is actually equals to this half base multiplied by the perpendicular height. So in this case, what would have there, it would be half. In this case, the base, which is delta t, multiplied by the force, which is F net, right? So in this case, what we know that, of course, the time, so this is actually the time, which is 0.5. So this would be a half multiplied by 0.5. In this case, multiplied by, let me just rewrite that. So this would be 0.5 multiplied by, in this case, the net force, which would be 150. Now, by the way, this is, just a coincidence that we have here. It's not always going to be like that. So in this case, the answer that you're going to get there would simply be, in this case, 37.5 Newton second. Now in this case, they just simply asked for the for the magnitude. They didn't want us to concern ourselves about, in this case, the direction, in this case, of impulse. So in this case, that would be our answer for that question. Now there is actually another interesting thing on this chapter. This chapter, it actually also kind of intertwined with Newton's second law. Now let's just go back to grade 11 for a bit. Now, if you remember, in grade 11, that line is very skewed. That line is very skewed there. Now, let's make it, not very skewed. So we have that. Now, if you remember from grade 11, you learned about Newton's, second law, which says that F net, so that's Newton. So that's Newton, in this case, second law, right, which states that F net is actually equal to mass multiplied by the acceleration. Now, how would we calculate, in this case, the acceleration normally? So in this case, normally we would say that acceleration is actually equal to the change in velocity divided by the change in time, right? So in this case, if you expanded that, what would have in this case would be Vf minus Vi, all of that divided by delta t. So in this case, in terms of A, so what I'm going to do would be to substitute Vf minus Vi divided by time. So what I would have there would simply be the mass, right, multiplied by, in this case, Vf minus Vi divided by delta t. So in this case, if we even expand that even more, now remember that this would be over 1. So in this case, what would happen here is that the numerator would multiply by the numerator. In this case, the denominator would actually multiply by the denominator. So what I would have in this case would be a mass. I'd multiply by Vf minus Vi. Alright, that's right. So this will be multiplied by Vi. So in this case, this will simply all over be all over in this case delta t. Now, as you can note that this is actually the change in momentum of an object. So in this case, what I would have there, now that's not good. Right, so in this case, what I would have there would be change in momentum divided by delta t. So in this case, this will simply still be equals to what? To F net. Now this, ladies and gentlemen, what we have right here is Newton's second law in terms of momentum. So that's Newton's second law in terms of momentum, which states the momentum, which states that the net force acting on an object is equal to the rate of change of momentum. So that's your formal definition. Again, you need to know that definition. I'm not going to write it down. So that's one definition again that you need to note when, again, these definitions, they come, a lot. So in this case, so this is Newton's second law in terms of momentum, which states that the net force acting on an object is equal to the rate of change of momentum. Now please note very importantly about this about this formula, that if you increase time, what happens to the net force is that the net force decreases. But if you decrease the time, so in this case, now a few things that you need to note, I'm simply going to write that down. So in this case, this would be NB. All right, so things that you need to note is that an increase in time, in this case, decreases the net force. In this case, given that the momentum remains the same. And again, the second thing is that a decrease. In this case, a decrease in time. The smaller the time, in this case, the bigger. The bigger in this case. No, I hope that's bigger. The bigger in this case, the net force. So in this case, the bigger the net force. So those are the two things that you need to know. Now, of course, this would be given that, of course, momentum remains constant. So what you need to note very importantly is that the smaller the time taken over which the force is in contact with your hand, in this case, the larger the force and the more the pain. Now, this is where safety precautions really comes from. Now, listen to me. This is very, very important, ladies and gentlemen, because Sir Mike is about to save your life right now. So this next part is very important, especially for those of you, who are in very strict rules. So when someone says, when someone says, give me your hand for punishment, I would say congratulations if you have made it at this point, because right now, you are inside a physics experiment. Now listen to this. This will save your life one day. So according to Newton's second law in terms of momentum, this is what it tells us. The shorter the time, the bigger the force. So if you put your hand in one fixed position, boom, very small time, big force, big pain, big time. But if you are smart and use the laws of physics, you move your hand in the same direction as the net force, the lesser the pain. So if there's a force going down towards your hand, you go down to at the time of contact. Why? Because in this case now, what you are doing in this case, you are increasing, because now the stopping time in this case it increases, and when time increases, the force decreases, and that, ladies and gentlemen, is Newton's second law in terms of momentum, saving lives. Now, jokes aside, again, this is how this is exactly how safety devices works, like airbags, seatbelts, helmets, or catching a ball and bent hands, right? So they all increase the time of impact and reduce the pain, and reduce in this case the force, minimizing the the injuries. So increase the time, you save your life. So what I'm saying is that if you can't reduce the change in momentum, people just increase the time. Physics is not just for exams. Sometimes it's it's for survival. So that's what we have. Very importantly, you must know that if you increase the time in this case, so the bigger the time in this case, the smaller the force, and then of course in this case the smaller the time, and in this case the bigger the force. Why? Because these two are actually inversely proportional. You increase the other, the other one decreases you, yeah, and then the other way around. So we have a question that we have here that actually consolidates everything that we have just discussed right now. Now again, I didn't want to do this question. Why? Because I didn't want to make this video a very long video. But anyway, let's just consolidate all the things that we just did. Right, so they say that the diagram below shows a 65.4 kg gymnastic dancer who jumped in the air and landed on her foot on the floor at 7 in this case yeah they say that the diagram below shows a 65.4 kg gymnastic dancer who jumped in the air and landed her left foot on the floor at 7 meters per second. They said that she slid and came to a complete stop in 0.5 seconds. So that statement there, let me just highlight that. So this statement, complete stop, so this tells us the final velocity in this case would be 0. All right, so I hope that makes sense. So that would mean that this is actually the initial velocity. So in this case, they said that define the term impulse in words. Now again, I'm not gonna write that down, unfortunately, ladies and gentlemen, but you must actually write it down when it comes in the in the exams. Don't leave it there as some belief. Right, so in this case, impulse, we said that impulse is the product of the net force and the time taken over which the force acts on the object. So that's your definition there. Impulse is the product of the net force and the time taken over which the force acts on the object. Right, so for 2.2, they said that calculate the impulse of the dancer. Now, two things we have learned. There are two ways to calculate impulse, right? We have already gone through that. So what you need to note is that if you look at the information that they gave us time, right, which is good, but they did not give us in this case the net force. So in this case, now remember, we have two ways, right, to calculate impulse. You could either use the change in momentum, or in this case, or the other one. But the other one in this case would require us to have in this case the net force, which is what we do not have. So in this case, what I'm going to do would be to calculate an object's change in momentum, and that would simply be in this case our impulse, right? So in this case, what I'm going to do would be to say that impulse, all right, so in this case this would be impulse would simply be equals to an object's change in momentum, right? So in this case, this would be mass multiplied, so this would be Vf minus Vi. Now what I'm going to do would be going to take upwards as positive and downwards is, in this case, is negative, because she jumped up and down, so that means that we are dealing with, in this case, vertical motion. So in this case, what would have in this case, this is, never mind, let me not even go there. Now I'm talking about vertical motion, like we are in vertical projectile motion. But anyway, let's leave that for later. So in this case, we know that the mass, so that's 65.4. So in this case, our final velocity is they say that she came to a complete stop, right? So meaning that the final velocity in this case would be 0, and the initial velocity in this case, it would be 7, but in this case positive 7. Remember that negative there is just simply the the part of the formula. So in this case, what we would have there would simply be our answer in this case would be, in this case, negative. In this case, so this would be negative. So that's negative. So that's actually negative. So it would be negative 65. No, actually, no, I'm lying. So in this case, this would be negative 457, right, 0.8 Newton second. So that would be that. Now remember that, of course, remember that our dancer in this case was in this case, so she jumped, right, and came to a stop. So in this case, she was actually moving in downwards. So that would mean that there is a force that is actually acting against her. So in this case, that would mean that of course the direction of that force would be upwards, right? So in this case, what would have here would actually be in this case 457.8, but in this case Newton second, in this case upwards. Right, so in this case I think there's something that I did wrong somewhere there. So in this case the answer was supposed to be in this case upwards, the direction, very importantly. Right, so in this case they say that for question 2.2.2 they say that calculate the magnitude of the net force which the floor exerts on the dancer's foot in this case. So now remember again, so what we're going to do, they say that calculate the magnitude, right? So that's another question down there, the magnitude of the net force. So what I'm going to do would be to use the impulse momentum theorem, which says that in this case F net multiplied by, let me just say, so that's for 2.2.2, right? So in this case what I'm going to say would be say F net multiplied by delta t, so that would simply be equal to, in this case, the change in momentum, in this case, which would be, in this case, this answer that we got there. So in this case, so since we now remember that of course the ground in this case would exert an upwards force, so in this case it would be positive, right? But in this case, the dancer, the ground exerts a force upwards, but the dancer in this case she exerts a force downwards, right? So in this case, since we are focusing on since we want to know the magnitude of the force that which the floor exerts on the dancer's foot, so that would mean that the change in momentum that we're going to put there should be positive. Why? Because in this case the floor will be exerting the force upwards, meaning that its change in momentum would actually be upwards, right? So in this case what we are going to have there would be, in this case, F net, right, which is what we are looking for. So this will be F net multiplied by time. They gave us time to be 0.5, so this will be 0.5 multiplied by mass, all right, multiplied by the change, multiplied by Vf minus Vi, but we already know that of course this should be 457.8. so in this case this will simply be 457.8, right? So in this case if you divide by 0.5 on both sides, so what you're going to get would be F net being, in this case, 915, in this case 0.6 Newton, but in this case upwards, right? So that would be the answer for that question. Now again, I don't know why I concerned myself about that direction there. Why? Because they actually asked us to calculate the magnitude, not in this case the force alone, right? So in this case that would be how that question is done. Now for question 2.3 they say that the diagram below, in the diagram below, is 600 grams of football which is initially at rest. So that would mean that the initial velocity is 0, right? So they say that that ball is thrown at the wall, all right? So in this case they say that so what they said was so they said the following graph in this case shows the change in the applied net force over a period of time. So this is the graph that they gave us. So they said that state Newton's second law in terms of momentum. Now we have been through this, so we know that the Newton's second law in terms of momentum simply said that the net force acting on an object is equal to the rate of change of momentum. So that's would be for 2.3.1. so for 2.3.2 they say that calculate the magnitude of the impulse exerted on the to the football. Now again, you can note that we actually have that graph again. So in this case, to calculate impulse, what would be to say that impulse, so the impulse would actually be equals to, in this case, to F net. So so impulse will simply be equals to, in this case, a half, in this case base, multiplied by, let me just go back a bit. So this would be equals to, in this case, to the area, in this case, which is actually equals to half, in this case base, multiplied by, in this case, perpendicular height. So in this case what I would have there would simply be a half. In this case we know that the base in this case is time, so in this case we know that the change in time in this case would be 12, right, but multiplied by the force. So if you note, actually they're actually working with 10. So in this case from here to there, so that's 10 lines, from there to there that's 10, and that also that 10. So in this case, as you can note, we're actually at that point. So if we go in that line, let's see what would that number should be. So this would be, so just to be 30, 31 there, 32, 33. So that should be in this case 34. So what we have in this case, this would be 30. So that should be 34, right? And if you put that into the calculator, the answer that you're going to get would be in this case 204. So this would be 204. In this case, Newton second. Now again, we are not going to concern ourselves about the direction. In this case, why? Because they actually asks us to calculate the magnitude. All right. So in this case, for 2.3.3, they say that let's see. Let me just adjust that a bit so that the question shows right. So in this case, they said that use a calculation to show that the velocity at which the football hit the wall is in this case 340. Now remember, they say that this ball was initially at rest, right? So in this case, that would mean that its initial velocity was actually 0, right? So in this case, what we're going to do now, remember that we know in this case that since we know that, of course, impulse is actually equal to an object's change in momentum, so that would mean that the change in momentum of this object is actually equals to 204 kg meters per second. So in this case, what we'll do in this case would be to say that change in momentum is actually equal to m mass multiplied by Vf minus, in this case, Vi. Right. So in this case, we know that, remember, we have, so in this case, we know that, of course, the ball was, it started here, and then in this case it moved into that direction in this case. So what would, so in this case, the change in momentum should be positive. All right. So in this case, the answer for ours there, the change in momentum would be 204. So this would be 204. So this is simply equals to the mass. Now please note the mass, we should always substitute it there into our formula, in this case as in kilograms, right, as in kg. So in this case, they gave us in grams. So in this case, what we would need in this case would be to convert that. So 600 grams, so in this case in kg, that's approximately 0.6. You divide that by 1000. So in this case, what you would have is the mass. So this will simply be equals to 0.6. Now what you're going to do would be, now we are looking for the final velocity, right? So in this case, this would be Vf minus 0. So we know that initial velocity was 0, right? So in this case, this will simply be 204. So this will simply be 0.6 multiplied by, in this case, Vf, and you divide by 0.6 on both sides, and what you're going to get would be our final velocity as in this case 340, in this case, to the right, since we got that answer to be, in this case, to be positive, right? So that would be how that those questions are done. Now these are the questions that I've prepared for you to try out. Now remember that, of course, you master in concept by practicing. So pause the video, attempt the questions, and post your answers in this case in the comment section. I'll make sure to go through each and every one of them, giving you feedback. But otherwise, if this lesson helped you to understand even better, surely it can also help your classmates. So like, share, and subscribe if you are watching from YouTube. If you are watching from Facebook, also like, share, and hit that follow button so that you don't miss a new video when it comes up. But otherwise, ladies and gentlemen, as the story always ends, this is Mike signing out. Sharp.